Hello and welcome to our lesson on derivatives and rates of change. This is going to be from section 2.7 in our Calculus 1 text. Let's get started. First, we have the definition of the tangent line to the curve y equals f of x at a point. P a comma f of a is the line through P with slope. All right, look at what this says. M is the slope. It says it is the limit as x approaches a of the, what is this? It's the slope formula. y2 minus y1 over x2 minus x1. So if we take the limit as x approaches a, notice that would make the denominator approach 0, and the limit of this formula will give us the slope of the tangent line at this particular point of the function. Okay, that's what this says. This is another version over here. It says the limit as h approaches 0, and you may realize what we have here is the difference quotient. So if you were wondering in college algebra, when are we ever going to need or see the difference quotient? Here it is. And what is it used for? It is used to find the slope of the tangent line to a curve at a point, okay? That's the summary of the entire lesson here. Now, let's look at an example of this in practice. It says, find an equation of the tangent line to the parabola, y equals x squared, at the point 1, 1. So if I want the slope of the tangent, what that is the limit as x approaches a. Now a is an x value, which is going to correspond to the x value of the ordered pair that you're concerned with where the tangent line goes. And so our a that we're approaching in this case is 1. And then we set up the slope formula, y2 minus y1, or in this case it says f of x minus f of a, which a again is 1 over x minus a. F of x is our function. F of a is the function value at a, all over x minus a. And then one step of simplification. We have the limit as x approaches 1 of x squared minus 1. Okay, time out. Notice that is the difference of squares. Let's factor on the fly. X plus 1. X minus 1, difference of squares. Notice what that does for us. Before, if we wanted to calculate this limit like at this step, with direct substitution, we would have an undefined situation. But now that we have the numerator factored, we can eliminate the undefined situation and then calculate the limit with evaluation. Evaluating x plus 1 at 1. 1 plus 1 is 2. Now what is this? This is the slope of the tangent. If I have a point and a slope, I can use point slope form, which is y minus y1. Where did that come from? Right here. Equals m, parentheses, x minus x1. That is your answer if it says to write the answer in point slope form. Most problems say put the answer in slope intercept form. So in that case, we need to keep going. We're going to distribute the 2 and bring the negative 1 over. That's going to give us a 2x minus 2. Hang on, negative 2 comes over and makes a plus 1. Negative 2 plus 1 is negative 1, and we're done. That is the equation of the tangent line to the parabola at the point 1, 1. And then what would be awesome is if we went to Desmos and verify that. And with just a few button clicks here in Desmos, we have our answer validated. See, the red graph is the function y equals x squared. I have plotted the point where we wanted the tangent line to touch the curve, and we can see that our equation of the tangent line does indeed do what it's supposed to. It is tangent. It does touch the curve at only the point 1, 1. Desmos is an awesome tool for verifying your handwritten work. Next, we have another example. Same song, second verse. This time our equation is a hyperbola. Y equals 3 over x, and at the point 3, 1. I think it's important to mention that this point that you're concerned with, it actually should be on the graph. And if you're not sure if it is, you can check. All you have to do is replace x with 3 and see if it equals 1, which it does, okay? So that point is on the graph. And if I want to find the equation of the tangent line, the first thing I need is the slope of the tangent. But at this point, the formula for finding that is the limit as x approaches a. Remember, the a is the x of the ordered pair you're concerned with, of f of x, which in this case is 3 over x, minus f of a, which would be 3 over 3, all over x minus a. And then we're going to need to see if we can evaluate this limit with direct substitution. Oh no, it's going to make a 0 in the denominator. So let's see if we can use our algebra skills to eliminate the undefined situation so that we can evaluate the limit with So let's see if we can eliminate the undefined situation so that we can calculate the limit with evaluation. Here we go. We've got 3 over x minus 3 over 3, which is 1, all over x minus 3. And then what I would like to do is get a common denominator with the 1 so that I can combine these terms in the top. So what is equivalent to 1 with a denominator of x? That is x over x. Okay, so that would equal 3 minus x all over x minus 3. And would you look at this? This numerator is almost the denominator. The only difference is that it is opposite. So what I would need to do to make it the same is factor. Let's factor a negative out of the numerator and then simplify. That will give us the limit as x approaches 3. Factoring a negative out of the numerator would turn that into Factoring a negative out of the numerator would turn that into negative 3 plus x, or x minus 3 over x. And then what I'm going to do is this. See how this fraction bar makes the fraction complex? I'm just going to kick this out to the side and say divided by x minus 3. And then maybe you can see that we need to KCF. That means we need to keep, change, flip. So we keep the first fraction the way it is, we change division to multiplication, and we flip the second piece. Now this is understood to be over 1. If I flip it, that would make it 1 over x minus 3. And then notice that that's going to allow us to eliminate the common factor of x minus 3. Which causes our limit to simplify to the limit as x approaches 3 of negative 1 over x. And now we can Now we can calculate the limit with evaluation, and we can see the slope of the tangent would be negative 1/3. If I have a point and the slope, I can use point slope form. So that's going to give us y minus y1 equals m, x minus x1. And then we probably want to put that into slope-intercept form, so we're going to distribute the negative 1/3 and move the negative 1 over. Y equals negative 1/3 x, negative 1/3 times negative 3 is plus 1. The negative 1 coming over also makes plus 1, CLT, which means combined like terms, giving us plus 2. And we're done. That is now the equation of the tangent line to this curve at this point. Oh, and you know where we're going, right? We're going to Desmos and check. And here we are. In Desmos, I have my function graphed with the point where we were concerned about the tangent line to the curve. And you can see that the equation that we ended up with looks perfectly tangent at that point. Next, we have another definition, this time telling us what instantaneous velocity is. Oh my God, did you see what we have here? This looks exactly the same as the slope of the tangent, okay? So the same formula that gives us slope of the tangent also gives us instantaneous velocity of an object based on its position function at time A. Whatever time you're concerned with, we can find the instantaneous velocity of a function by simply using the same formula that we used to find the slope of the tangent. And now let's look at an example. A cliff diver plunges from a height of 100 feet above the water surface. The distance the diver falls in t seconds, so t is time, is given by this function. And the distance, again measured in feet, it says after how many seconds, that means we're looking for time, will the diver hit the water? Well, how far above the water was he? 100 feet. Wouldn't that be his distance? So this is telling me that we need to replace d of t with 100 and solve for t. If it seems too easy, it actually is. It's too easy here. We're going to replace the distance with 100. We're going to solve for t. Dividing both sides by 16. And then notice all we have to do is take the square root to get rid of the squared. Lucky for us, before we reduce that fraction, those numbers are perfect squares. So the square root of 100 is 10, and the square root of 16 is 4, which again, that will reduce further to 5/2 seconds, since t is measured in seconds, or you could say 2.5 seconds. How long will it take him to hit the water? 2.5 seconds. That he has to consider all of his life choices before he hits the water, okay? Part B, with what velocity does the diver hit the water? This would indicate that we want to find the velocity when he hits the water. When does he hit the water? After 2.5 seconds. So we want to find the velocity at 2.5. Do we have a formula for velocity? Heck yeah, we do. It's the same as the formula for the slope of the tangent. So let's plug into this formula and make it work, okay? All right, here we go. All right, here we go. So this is going to be the limit as h approaches 0 of If we go back and look at the formula, it says f of x plus a. F of, well, x in this case is t. A in this case is 2.5. That would be f of t plus 2.5 minus f of t. Okay, fine. It's not actually f. Remember, it was d. Function was in terms of d. Doesn't really matter, okay? But trying to be nice. All over h. Can we evaluate this limit with direct substitution? No, because the h in the denominator would go to 0 and we can't divide by 0. So again, we're going to try to use our algebra skills to simplify this expression so that we can get this h to cancel, and then we can evaluate the limit with direct substitution. So what was the function? D of t was 16t squared. So this is going to be the limit as h approaches 0 of 16t, in this case, is so this is going to be the limit as h approaches 0. The formula said f of a plus h. Well, remember, f in this case is d. A in this case is 2.5 plus h. D of 2.5 plus h minus d of t. Minus d of a, which is 2.5, all over h. And we're going to need to simplify this expression. Hopefully we can eliminate the h in the denominator so that we can evaluate the limit with direct substitution. All right, here we go. That's going to be the limit as h approaches 0. D of t was 16t squared. So this is going to be 16, 2.5 plus h squared, minus 16 times 2.5 squared, all over h. And then that's going to be the limit as h approaches 0. We're going to need to FOIL. This right here, squared, means we're going to have to FOIL that. So 2.5 times 2.5, 6.25. On the outside, we'll have a 2.5h. On the inside, another 2.5h. Together would make 5h plus h squared. That's doing the FOIL mentally, quickly. Minus 2.5 squared, 6.25 times 16. I think that works out to be 100. All over h equals the limit. As h, notice I keep writing the limit notation until I can calculate the limit with evaluation. We need to distribute. That's going to be 100 plus 5 times 16 is 80 h plus 16h squared minus 100 all over h. All right, here we go. Now it's getting close to the end. The hundreds cancel. The remaining terms both have an h, so I can factor out an h, which will leave me with 80 plus 16h over h. And the h's can now reduce out. And now that I'm not going to have an undefined situation, I can calculate this limit with evaluation. Any other h goes to 0. We can see we're going to be left with 80. So what did we actually find? The velocity after 2.5 seconds. The velocity when he hits the water is going to be 80 feet per second. That is the answer to this question. Next, big concept coming up right here in Calculus 1. We finally get to the derivative. It says the derivative of a function f at a number a. This is the notation. Let me zoom in on that real quick. This is read f prime of a. F prime of a, this is the first derivative of the function at a, can be calculated by the same formula that we use to find the slope of the tangent. So this is a super important concept, that the derivative is the slope of the tangent. Say that with me. The derivative is the slope of the tangent. Does it go the other way? Hell yeah. The slope of the tangent is the derivative, if it exists. All right, let's look at an application of finding the derivative of a function. Here we have an example. It says, find an equation of the tangent line to the parabola y equals x squared minus 8x plus 9 at the point 3, negative 6. All right, so if we want the equation of a tangent line, doesn't that mean we need to find the slope of the tangent? But now we know that the slope of the tangent at a particular value is really the derivative at that value. See, our value in this case is 3. So when we're going to find the equation of the tangent line, we're really going to find f prime of 3. We need to know what that works out to be, and that'll be the slope of the tangent. Here we go. That is the limit, as x approaches 3, of f of x, which is x squared minus 8x plus 9, f of x, minus f of a, which says plug in 3 into all of those x's. And so that'll be 3 squared minus 8 times 3 plus 9, all over x minus a, which in this case is 3. All right, did you notice that I am using this first formula? And I tend to use this particular formula when you're trying to find the slope of the tangent at a point. This would not be the formula I would use for finding f prime of x, okay? Even though this formula over here works to find a derivative at a particular point, this is actually the formula that I would use to find the generic derivative, and instead of a value, here you would have x in both of these cases, okay? So I tend to not use this formula for finding the slope of the tangent, although you can. So if we continue our work here, we have the limit as x approaches 3 of x squared minus 8x plus 9. And then we need to figure out what is this function value. So we're going to use the calculator. 3 squared minus 8 times 3 plus 9 is negative 6. Minus a negative, do you see that's going to be minus a negative 6? So that'll actually end up being a plus 6. Oh, look at that. I've got like terms. 6 and 9? What is that? 15? All over x minus 3. I hope you paid attention there. I did some simplification on the fly to end up at this result. And now can I calculate this limit with the valuation? No, because I get a 0 in the denominator. So let's see if we can take the numerator and f it up so that we can simplify. You know what F word that is, right? Factor. If I read the signs, they're both going to be negative. x and x to make x squared. What about numbers that multiply to make 15 that add to make 8? Well, that's 5 and 3. And lucky for us, that does match the denominator. So we can reduce out the common factor of x minus 3 and evaluate the remaining expression at 3. So what the limit as x approaches 3 of this function is going to be 3 minus 5. Oh, wait, that's really the slope of the tangent. 3 minus 5, that's negative 2. Are we done? No, because we haven't found the equation of the tangent line. But now we do know a point and a slope, so we can use point-slope form. Y minus y1 minus a negative makes it a positive equals m, which is negative 2, x minus x1. And we're done. If you want the answer in point-slope form, but I would rather have the answer in slope-intercept form. So we're going to need to distribute and bring the 6 over, giving us negative 2x plus 6 minus 6. Oh, look at that. 6's are gone. And our equation of the tangent is super simple. Y equals negative 2x. And I could go to Desmos again to verify that, but I'm getting lazy now. I'm going to skip that. Next, more information. The difference quotient, the rate of change of the y's related to the rate of change of the x's. Okay, this is the change in y divided by the change in x. Do you see what that really is the slope formula. This is called the average rate of change of y with respect to x over a given interval. So this would require that you have 2 points on the graph, giving us the average rate of change. However, the instantaneous rate of change is the limit as the change in x's approaches 0 of the same formula. So if x2 approaches x1, notice then the denominator would approach 0. And whatever the y value is there, whatever that limit approaches, is going to be our instantaneous rate of change. Okay, do you understand? That is the rate of change at a particular point. The average rate of change is the speed or the velocity or the rate of change over an interval. But the instantaneous rate of change is at a specific value as x2 approaches x1. And then what do you need to get out of that? The derivative is the instantaneous rate of change. Not only is the derivative the slope of the tangent, it is also the instantaneous rate of change of a function with respect to x as x approaches some value. And then in our exercises, we have several problems to look at that would illustrate that I'm not going to cover here. If you need some examples, videos of examples that see how that work, I highly recommend that you check out a couple of other YouTubers do great videos illustrating these examples. But that's going to do it for me in this lesson. So if you have any questions or comments about anything covered in this video, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.